My name is Aleksandr, and I work as a senior software engineer at GridGain. And today, I would like to tell you about discovery and cluster membership and how their implementation in Ignite 3 is different from Ignite 2. Let's start with outlining what this talk is going to be about. I'm going to start with an overview of the discovery component and how it works in Ignite 2. This will not be a thorough overview, though, simply because I don't have enough time for it in this talk, and there exist plenty of wonderful talks by other people and other materials. After that, we're going to see how this component has changed in Ignite 3, what protocol it uses, and how the cluster is organized overall. First of all, let's define what a discovery component is and what duties it carries out. The main responsibility of this component is to be a part of the cluster membership protocol implementation. That is, it must provide every node with a locally maintained list of alive members of the cluster, along with some meta information about these members. By locally maintained, I mean locally in regards to the node on which the protocol is running. In other words, this component ensures that newly added nodes appear in this list and failed nodes get dropped from this list. In Ignite 2, it also serves a second purpose. It provides the ability to deliver globally ordered messages, which can be helpful in a distributed system when we need to prevent some concurrent events from happening in an unidentified order. As we will see later, the cluster membership protocol heavily relies on this property. Okay, since now we know what the discovery component is, let's see how it works in Ignite 2. There, all nodes are organized into a one-way ring topology, and the oldest node is granted the role of the coordinator. By oldest, I mean the first node that has joined the cluster historically. These are the building blocks that allow us to achieve the global message ordering I was talking about. So any message that is sent through the discovery subsystem travels across the ring until it reaches the coordinator. The coordinator then marks it as verified and sends it for another go around until it comes back. When the coordinator receives the verified message again, we can safely assume that it has been delivered to all nodes in the cluster. Until a message is verified, it does not modify the cluster state, and this helps to ensure that every node only sees messages in the same order as they are processed on the coordinator. Now let's have a look at other responsibilities of the discovery component, namely how a view of alive nodes is maintained. And first, we're going to discuss how new nodes appear in this list, or how new nodes join a cluster. Here on the slide, we can see a cluster with 3 nodes, and they are organized into a ring as I was talking about. Now, let's introduce a new node, node number 4, to our cluster. To do that, the joining node sends a join request to a node that is already a part of the cluster. In order to do that, node number 4 uses a special component called an IP finder, which is basically responsible for providing an initial list of addresses of the nodes in a cluster or in a future cluster. There can be different implementations of this component. For example, it can use a hard-coded list of addresses, or it can get a list of addresses from a cloud subsystem. Nevertheless, here node number 4 decided to send a join request to node number 2. And when the node number 2 receives the join request, it forwards it directly to the coordinator. The coordinator then generates a special message called node edit message and sends it across the ring. So this message travels across the ring until it reaches the last node in the topology. Here it's node number 3. And node number 3 knows that it is the last node in the ring. So it adds the new node, node number 4, between itself and the coordinator, and then sends the node edit message to the new node. The new node then forwards the request back to the coordinator. So node number 4 is logically in the ring now, but it's not yet added to the topology. When the coordinator receives the message back, it generates a new message to finalize the process of the join of the new node. And this message is called node add finished. So this message is sent across the ring. It visits every node, and when it completes the full circle and coordinator receives the message back, the join process has been finished and the new node has successfully joined the cluster. Now we know how new nodes get added to the list of alive members, but when do they get removed from it? If a node does not leave the cluster gracefully and fails for some reason, then it needs to be removed automatically. This is called failure detection, and in Ignite 2 it is implemented on top of periodic sending of heartbeats across the ring by the coordinator. Then a node can be declared faulty due to one of the following reasons. Either if a node is unable to send a message to its neighbor in the ring, or if the coordinator has not received the heartbeat message in a while. If any of these things are true, then the coordinator initiates the removal of the failed node. Let's see how it happens. Here's our cluster from the previous example. We already have 4 nodes there, and now imagine that the node number 3 has died or became unavailable due to a network partition. Let's say that in this situation, node number 2 is unable to send any messages to node number 3 and detects this problem. When it does that, it generates a message called node failed message and sends it across the ring to the coordinator. As it travels the ring, every node marks the probably failed node as unavailable, but it's not yet removed from the topology. When the message is delivered to the coordinator, it verifies it and sends it across the ring again, and this time the node is treated as faulty and is removed from the topology. Before we continue to discuss in Ignite 3, I have some final words about discovery in Ignite 2. As we have seen, all messages have to travel across the ring at least twice, or for some actions, the protocol requires sending of multiple messages. This is not a problem in terms of network throughput, because the messages are very small, but this increases the overall latency of the protocol, especially when you have like 1,000 nodes in the cluster. The solution to this problem is to use an alternative discovery component implementation that uses a separate Zookeeper installation, but that comes with the cost of having to maintain a Zookeeper cluster on top of the Ignite cluster. Now, having discussed Ignite 2, let's dive into discovery in Ignite 3 and what happens there. First of all, the discovery component is no longer used to deliver ordered messages, since different components of Ignite 3 use a replication protocol based on Raft, which provides the same guarantees on its own. Secondly, the membership information, and as you may remember, membership information is about maintaining a list of alive members of a cluster. This information is provided by a protocol called Swim. However, as we will see later, Swim provides a weakly consistent view of the topology on every node. So in case we need to have a strongly consistent view, Ignite 3 uses a different topology, which is built on top of both Swim and Raft. This may sound quite complicated, so let's dive into some details. First, let's find out what Swim is. This is a cluster membership protocol, and unlike the protocol in Ignite 2, it is decentralized, and its latency increases logarithmically in regard to the cluster size, not linearly when we were using a ring topology. Now, Let's see how Swim works and how it maintains the list of alive members. Adding new nodes to the cluster is quite straightforward. A joining node uses the same IP finder component that is ported directly from Ignite 2. So it uses this IP finder mechanism to get a list of initial nodes and sends ping requests to those nodes, providing the information about itself. Those nodes then, when those nodes receive the ping requests, they further spread the information to other members in the cluster. However, failure detection is a bit more tricky. Let's have an example. Let's take a cluster with 4 nodes, and every node has a special period of time called the protocol time, and at these given intervals, it chooses a random node from the list of alive members and sends a special ping request to this node. So in this example, node number 2 chose the node to ping node number 1, and let's imagine that node number 1 is actually dead, so it's unable to respond to node number 2. When node number 2 detects that, using a timeout, it asks other members of the topology to ping this member indirectly. So it sends the same ping request to other members, but asks them to forward it to node number 1. This is needed because node number 1 might not have died, but instead it is simply unavailable to node number 2 using its communication channel. So to help us with network partitions, we're trying to probe the node indirectly using other nodes. But since node number 1 is actually dead, it's unable to respond to other nodes as well. So these nodes also time out and they return an error to the originating node, in which case the failed node can be declared faulty and it is removed from the list. I'm also going to briefly describe some other Swim concepts. The first one is infection style dissemination, which I briefly mentioned when discussing how nodes join the topology. This means that all these ping messages and acknowledgement messages are not only used for protocol purposes, like probing the nodes, but it also used to spread information about dead and alive members as they are seen by the sending node. The second concept is called suspicion, and it is aimed to reduce the number of false positives when declaring some nodes as faulty. So instead of removing an unreachable node immediately after it couldn't be pinged even indirectly, we start to suspect that node. And this means that we have a special list of suspicious nodes that is propagated to all other members of the cluster. And then either some node is able to ping this suspicious node, or after a timeout, we can say that all hope is lost and that node is dead and it should be removed. Unfortunately, though, Swim doesn't cover all use cases that we have in Ignite 3 because it is really consistent. What it means is that at a given moment in time, local membership lists on different nodes may differ, even though they will eventually converge to the same value. In order to solve this problem and provide a consistent topology view, we use a raft. And a special raft group called Cluster Management Group, or CMG for short. This group is created and configured during a special phase called init. I'll show you how it works using an example. Here we have a cluster that consists of 3 nodes, and they have been assembled together into a topology using Swim. Now we use a command line tool that comes as a part of Ignite 3 to send a special command called the init command. It can be sent to any node in the cluster, and it is used to specify addresses of the nodes that will host the CMG. Here, we are sending the init command to node number 2 and tell it that node number 1 and node number 3 should host the CMG. Node number 2 receives the command and since it is not part of the CMG itself, it simply forwards the request to the target nodes. Then node number 1 and node number 3 receive the command. They start the Raft group, elect a leader, and when all the stuff is performed, after this stuff has been performed, they return a successful response to node number 2. If everything is okay and all nodes responded successfully, then node number 2 returns a successful response to our CLI tool, and that's how we know that the init phase has completed successfully. Now we know how CMG is configured on a cluster, but what does it actually do? First of all, the leader of the CMG group is responsible for properly introducing new nodes into the cluster. It does that by listening to the changes in the topology, which is provided by Swim. We call it physical topology. And when a new member is detected, the leader validates the join requests and adds them to a topology persisted in the Raft state machine. We call it logical topology. Using Raft also allows us to propagate topology changes to other nodes in the cluster. Let's have a look at an example. So here we have two nodes in a cluster which has already passed the init phase, and all these nodes host the CMG group. And let's say that node number 1 is the CMG leader. Now a new node comes to the physical topology. It is detected by Swim, and the leader gets notified of a new member appearing in the physical topology. When that happens, the CMG leader sends a cluster state message to the newly joining node, providing some vital information, for example, where the CMG group is located and a cluster tag, which is needed to prevent the node from joining the wrong cluster. The joining node uses this information as part of its startup procedure, and after it is complete, it sends a join request to the CMG leader. The CMG leader validates this request and checks that the node can be safely let into the cluster, and if everything is okay, responds with a successful message. However, since the joining node might need to do some recovery or some catching up to get the newest data, which can take some time, and during that time the node is unavailable to user requests, it is not immediately added to the logical topology. But instead, we just wait until the node recovers, and then it sends a join ready request. When the CMG leader receives this request, it can safely add the new node to the logical topology. After the node joins the logical topology, it is registered as a non-voting member of the CMG. This means that it receives all updates from the changes in the Raft state machine, but it does not interfere with the replication factor and leader election latency. Removing nodes from the logical topology is much more straightforward, as CMG leader simply removes all nodes that are reported faulty by Swim. That is all I have to say, and here's a quick recap of what we have discussed today. So both Ignite 2 and Ignite 3 have a discovery component which is responsible for providing cluster membership information. In Ignite 2, it is also used to deliver ordered messages. Ignite 2 can use two implementations of the discovery component, a native one, which organizes nodes into a ring, and a zookeeper-based one. And finally, Ignite 3 has a more complicated approach, and it uses two mechanisms for representing topology information: a physical topology backed by Swim protocol and logical topology backed by Raft protocol. Thank you for your attention, and if you have any questions, I'll be very glad to answer them.
Thank you, Aleksandr, and welcome back to the stage. So we do have a couple of questions which we'd like you to answer. So get your question answering hat on. Here is the first one. So how should you choose how many nodes should host the CMG?
Well, I would say that since the SIMG is crucial for the cluster to remain operational, but I mean, if the SIMG loses majority, and the rough majority is like half of the nodes plus one. So if Raft loses majority, it's not able to function properly, and no nodes will be able to join the cluster, and the topology subsystem will break. So you don't need many nodes for performance reasons. You just need enough nodes in order to survive some crashes. So it depends on your concrete use case here.
Okay. Then the next question, do you need to initialize the cluster every time after a full restart?
Nope. This is like a one-time operation in the lifetime of a cluster. You can perform multiple inits with the same parameters just for the idempotency, but it doesn't change anything. So you need to call init only once.
Okay, great. We've got a couple more questions coming through in the chat. Alexei asks, is this new cluster membership mechanism available in beta 1?
Yes, thank you for the question, but actually I don't remember because beta 1 was released quite a while ago. It may be, but I don't actually remember. I need to check.
Okay, we'll have to get back to you on that one.
Yeah.
Another question from Dennis. How is the oldest node in the cluster identified in Ignite 3? And is this significant?
Yes. I think, well, in Ignite 3, we don't need to know which node is the oldest, because in Ignite 2, the oldest node is the coordinator, but in Ignite 3, we don't have a coordinator. Well, we have a coordinator, but it's the leader of the SIMG Raft group, and Raft doesn't care about the the age of the nodes. It has its own leader election mechanism.
Okay. Heads up, there's a few more questions coming in. Does Swim work in a network where ICMP is disabled?
Again, I need to check this one. I'm not sure if our Swim implementation, which we're using, uses ICMP packets for its ping requests. So they're called ping requests, but they do not necessarily have to be actual ping messages. So it can be like a UDP or TCP message, which we simply call ping. So I need to check with the implementation. I don't know right now.
Okay. Question from Kevin. With Ignite 3, is there a need to use Zookeeper from a performance perspective?
Ignite 3 doesn't. Thank you. Yes, thank you for this question as well. Ignite 3 doesn't support Zookeeper-based discovery, so you can't use it. And right now, it looks like we don't need it at all. So the idea was to get the best of both worlds from Ignite 2 implementations.
Okay. Question from Nikhil. Do you have to have a separate node for CMG, or does any one of the nodes in the cluster can act as a CMG?
This is an interesting question, and the answer is any node can host this. So the CMG is it obviously consumes some resources, but not much. It is just needed. So the leader of the CMG just validates some stuff and responds to some messages. So it's a bit more busier than all other nodes, but it shouldn't interfere with your other needs like querying data or something. So you can have a separate node if you want to, but it's not required.
Great. Okay. Next question. Hi, Alexander, from Dmitro. Hi, Alexander. We have a question on Ignite 2. We're experiencing random node failures and failed nogload messages points to the cluster coordinator. What can you recommend to get to the root cause of the failure? You're going to have to make this quick.
Well, I think our expert sitting in the special booth is a perfect person to solve these problems, because we need to have a look at the logs. I don't think we have time for this right now.
Dimitro, I can certainly recommend that you come to GridGain for some consulting or some support, and we can certainly help you out. So, last question then from Swapnil. Can we customize the topology and its failover parameters? Does it support any federation protocol? What he means by this is, does the Raft CMG support federation? That's the first question.
Thank you for that's a bit of a mouthful for me. Need to read it carefully. I don't think I understand the question properly. So maybe you could clarify, what do you understand? What do you mean by the federation protocol?
Swapnil, maybe you can elaborate on that.
And the second part about customization, it's customizable, so you can customize the timeouts and other stuff if that's really needed. Yes.
Okay. Well, let's leave it there. More information to follow, I think. Alexander, thank you for that. Thanks for the talk. As I said before,
I think there's also a second question in Swapnil's message.
do you want to pick up the second question quickly?
Yeah, sure. We're planning to. I'm not sure. We're definitely planning, but we need to support some like cloud providers. So we can use console as an IP finder. That's the stuff that I was talking. The component that provides the initial set of addresses, and I think console can serve a perfect role for that.
Okay. Swapnil has elucidated a little bit with the following comment. So I'm not sure that helps you answer the question.
So you mean like we have a situation when like one node is in one data center and the other node is in the second data center, and they all host the same G group. This scenario is not yet supported. So currently we need these nodes to be in a single data center. Maybe in the future that will change, but right now it's like that.
Alexander, thank you for the talk. Thanks for joining us on stage, and look forward to hearing.
Thank you for having me. Thank you for the wonderful questions. They were very cool.